All right, our next up is a talk from one of our sponsors, MathWorks. The talk is entitled Standards Compliant Digital Engineering, presented by Ossi Saarela. Ossi? We can see your slides. I think, are you?
No audio is coming through, Ossi,
Yeah,
although
you
you're
might...
not marked as muted. Not yet.
Stand by. Okay, it looks like you're no longer muted, but I haven't heard anything yet. For all the sound checks that we've tried to do. Oh. Nope. So I've heard frequently this notion of a double mute. I've never had it. I don't think I've ever had it happen to me, but that could be what's going on here.
Can you hear me now?
There we go. Okay, great.
All right.
Welcome, Ossi.
Do not know what happened between the sound check and now, but looks like we're back on track. So my apologies. I will start again. So as Chris said, my name is Ossi Saarela. I'm the Space Segment Manager at MathWorks. And while I can't speak for the rest of you, I know that I didn't join the space industry because I had a passion for working with standards. I joined because I wanted to innovate and build exciting things, as I suspect all of you do. And certainly when I started my career over 20 years ago now, testing software for the International Space Station, I cared a lot more about how the software behaved than how it complied. I didn't really give that much thought. Now, by the time I switched to working at MathWorks 18 years later, I'd seen a satellite I worked on blow up on the launch pad. I'd seen an algorithm that I designed fly, and a year later, I learned that it worked by accident, not at all the way I intended it to. So I think over time, as we see more things go wrong, as we assume more responsibility, standards become increasingly important, especially working on Class A, Class B programs. And these days also, even if working on crewed space in the private sector. So why am I talking about standards from the context of digital engineering? Well, these days, you can't help but be bombarded by buzzwords like digital transformation, digital engineering, model-based everything. And all of these things promise to disrupt our processes and the way we do things. So I thought it was timely to discuss how they interplay with standards, which also define our processes and the way we're supposed to do things. So next slide, please. So I'm going to start by kind of laying out the general overview of software standards landscape in our industry, which is not crystal clear, believe it or not. Then I'm going to talk a little bit about digital engineering, first of kind of the grand vision of all the things that's promising, but then also trying to narrow in on what pieces of it can we realistically adopt today with the tools that we have available for flight software design and implementation. And at the end, we'll kind of see how it comes together. Next slide, please. Okay, starting with standards, next slide. So software issues were recognized very early in the history of spaceflight. While people were celebrating the success of the Apollo 11 lunar landing, in the background, the infamous 1200 series computer alarms during the Apollo 11 descent that rebooted the LEM guidance computer multiple times, encouraged NASA to address the software engineering approaches used in the agency. Next slide, please. And over time, through a series of initiatives and workshops, this eventually led to the publication of the NASA Software Engineering Requirements, NPR 7150.2. And of course, the Software Safety Standard and Software Assurance Standards that go along with it. Next slide, please. So standards really don't have anything magical in them. They tend to reflect common sense. They promote best practices, lessons learned, like I mentioned. And they also evolve to incorporate new requirements as technology evolves. A couple of examples of this might be both the European ECSS and the NASA standards have sections dedicated to automated code generation, which is a relatively newer technology. And the latest release of the NASA NPR 7150.2, released in 2019, now also has a section in it that talks about cybersecurity, which is an emergent topic for us. Next slide, please. Now, in some industries, engineers will find their counterparts in different countries, different parts of the world, for the most part, speaking the same language when it comes to standards. You'll notice the three industries I'm highlighting here: automotive, medical devices, aeronautics. Those are all industries where just like in our industry, safety is of paramount importance in product assurance. Next slide, please. So in the space industry, things look a little bit different. Our software standards tend to vary by region or by country. They can vary by customer. If you have a government customer, they may vary depending on whether that's a civil or other government customer. But for government-sponsored missions, I would say the picture is the clearest, right? You tend to use the standard of your sponsoring agency. So in Europe with ESA, that tends to be ECSS. And here in the US with NASA, it tends to be NPR 7150.2. Now, in the private sector, the picture is a little bit more complicated. The private space segment is intentionally deregulated in the US to promote innovation, and that's been working very well. And there are some companies that are able to operate with a highly risk-tolerant business model that don't really need to worry about standards compliance. For example, if you were designing to fly and operate a mega constellation, the reliability of any individual satellite becomes less important, just due to the amount of redundancy you have built into your system. Now, there's certainly other private players who either have less risk-tolerant customers or who are working on high-integrity missions like crewed spaceflight. And those companies are looking at kind of the broader standards landscape and choosing what makes sense to them, including, in some cases, perhaps taking a look at some of the standards from the other industries that I mentioned to use as a basis. Next slide, please. Now, today we're in this interesting situation where we have a lot of private development, like I mentioned, some of it very, some of it not so risk averse, but we also have kind of a continuation of the legacy of ISS, where we have very complex multinational projects like Gateway, and certainly Human Landing System also has multiple vendors from different countries in the supply chain. And it's expected that multiple vehicles from multiple providers will need to work together, for example, to dock with Gateway or rendezvous with Orion. So in a way, the role of standards is increasing because these systems all have to interoperate. Now, will the International Deep Space Interoperability Standard that I mentioned here provide a common software development process? No, it will not. It leaves that to the responsibility of each organization using the standards I already mentioned. Next chart, please. But I thought it was worth at least mentioning these standards at this particular workshop because CFS, Core Flight System, is explicitly called out as a software framework. And I'm sure we'll hear a lot more about CFS as the workshop goes on. Next slide, please. So standards, when it comes to development standards, typically establish what should be done, not necessarily how to do it. This chart shows a high-level progression of the design flow that we know and love. Next slide, please. And here I've aggregated some of the actions or expected tasks from the relevant standards to paint a picture of what is necessary to do at each state of development to comply with these standards. And this isn't a comprehensive list, but this gives you an idea. And of course, the required activities also vary by mission class, right? A and B missions are much more stringent than say a Class D. Next slide. But nevertheless, you can see that there are a lot of things to do. So over time, we've established a gated process that ensures that all the things we're supposed to do before a certain step actually get done before we move on to the next one, so we don't get ahead of ourselves. Next slide, please. And of course, in this day and age, as we already heard, we're layering methodologies like Agile on top to see how those fit. We're adopting continuous integration and playing around with that. So this kind of is a high-level context of the world of software development that we know and love that maps these activities that we do to the standards that they came from. Next slide, please. All right, so let's take a look at digital engineering and examine how that's changing this landscape. Next slide, please. So first, let's talk about some of the motivations for digital engineering. So I would say that the flip side of the evolution of our processes and standards over time is that we have kind of ended up with corrective action layered upon corrective action in our quest to prevent failures and escapes in our system. And this has arguably led to a complex process that is document heavy and can be challenging to manage. There's a lot of moving parts that have to be kept in sync. Analyzing the impacts of the change on the rest of the system is tough, and it doesn't help that systems are continuously getting more complicated. Next slide, please. So how does digital engineering address these disconnects? One way is through the use of digital models. Next slide, please. So we're seeing an evolution in the industry which started out very hardware-centric and later, I would argue, pretty quickly became highly software-centric. I can't even tell you how many computers there are on space station already. And recently is becoming more and more model-centric. We hear about terms like model-based system engineering, model-based design, even model-based X, model-based based everything. And models are a way to explore systems before they're built. And they're also a way to provide abstraction from the system to help promote understandability. So you can be working on a single model, a single representation of the system that has different views to promote your understanding depending on your role. So a software engineer, for instance, kind of tends to live in the code level view of the system, but an algorithm designer or a system engineer might gain more value and be able to do their work better at a behavioral design level or even an architecture level of the same system. And we see this in different languages like UML, SysML, and of course here on the screen, you're looking at MATLAB and Simulink. Next page, please. So connecting the different parts of the system virtually through a common model or models is often called establishing a digital thread. But digital engineering, I think, has a bigger goal than just providing a digital thread. It really wants to enable the use of connected models throughout the life cycle to digitally represent the system in the virtual world. Next slide, please. And if you apply this consistently throughout the life cycle, the natural outcome is that you end up with a digital twin. And the digital twin is basically just the system in a digital form that is so close to reality that it can be used in place of the real thing to analyze and assess the system. And this, of course, is more than just a flight software level vision, right? This is a system level vision. But for it to work right, the flight software has to fit into this digital framework seamlessly. And certainly, my vision is that we can go from requirements to algorithms to prototype to accurate behavioral model to detailed implementation model, all the way to source code in the same environment without breaking the digital thread. Next slide, please. Now, when people hear about this concept, especially in our industry, people will say, well, haven't we been doing that all along? We know we can't fully test our spacecraft in a 1G environment on Earth. We've had to rely on modeling and simulation forever. Isn't that what you're talking about? And in a way, yes, but I would argue that the way we've traditionally done things is missing the digital thread, and that more complete system simulations usually only come together after the design is complete and you're doing either test integrations or operations phase level work. And before that, the ownership of the models and simulations is usually at the subsystem and domain level, and very, very few organizations are able to connect them early in the design cycle. So next slide, please. So we already heard an acknowledgement of Dr. Will Roper's paper. So Will Roper is the former Assistant Secretary of the Air Force for Acquisition and Technology. And his paper, Take the Red Pill, actually he had to change the name. It's now called There Is No Spoon, because he originally quoted one of two colors, red and blue, in an election year, which made it too political. So if you're trying to find the paper now, which I highly recommend you do, you will find it called There Is No Spoon, which retains the matrix analogy, of course. But in that paper, which is a short read, he lays out a pretty transformative approach of the future, and basically states that that we can go from the way we currently build and design systems, which is we design them, we build them, then we test them. And by the way, about half of a program's cost is usually spent in the integration and test phase. Next slide, please. To a concept of model, analysis, and build. Again, I encourage you to read the paper to kind of get into the details of this. My point is that there's a potential for a fundamental shift. I actually think adoption of this type of paradigm will be more incremental. I don't sense any appetite to get rid of the testing phases of the stuff that we build. But I think that there will be less and less time and effort invested in test and integration, because we'll be able to discover less, because there'll be less defects that make it all the way through into test if we emphasize modeling and analysis. Next slide, please. So that was a fairly future-facing concept. So now let's talk a little bit about what types of things can we do today that incorporate some of the concepts of digital engineering. And I would argue that two things that are probably well worth our time are trying to look for this digital thread, digitally connected modeling throughout our design life cycle, to get that single source of truth for our requirements, our data, everything, and also to automate tasks as much as is reasonable to improve our design efficiency. Next slide, please. So where does that take us? Next slide. Let's dive into these concepts a little bit deeper, starting with digital thread. So in the old way of doing things, if I wanted to say change an algorithm design description or a software requirement spec, I would have to go to a change board. The change board would ask me what else is impacted. I would say nothing else is impacted, but how would I prove that? Maybe I had a good reputation, they would believe me, I'd get to make the change. Next slide, please. But more often than not, the wise people on the change board would recognize that the impact analysis was a real challenge. It'd be tough to do. And because of that, we're kind of living in this world where, especially in the later phases of the design cycle, better becomes the enemy of good, right? We'll rather accept and live with a defect if we can bound it, right? We can devise operational workarounds, we can understand it, then try to fix it at the risk of inserting another defect that might escape us, right? Next slide, please. So the question is really, how can we further our understanding of the entire system when we're talking about the smaller pieces of it? Next slide. And this is, I think, where the digital model, utilizing the digital thread between components and depends and which already contains built into it these dependencies, can be very, very powerful. It can greatly improve agility, and it can break down that resistance to making improvements. So I would argue that searching for this digital thread as a single source of truth by use of connected models, all the way down to the flight software code, is a no-brainer for digital engineering adoption. Next slide, please. So let's talk a little bit about the automation piece. Now, we know that machines can fail. We know humans make mistakes. What kind of tasks are best automated? Next slide, please. So I think the key question here is, when is it more likely for a software tool to produce a correct output than a human? Certainly, I can write requirements or develop an architecture better than a computer. But if I'm cutting and pasting out of Excel into a database over and over, I can guarantee you that a machine can do that better and with fewer errors than I can. Another thing that is mundane and can easily be automated is documentation, whether it be test documentation, design documentation, inserting digital traceability of requirements. Those are all very good candidates. Automated code generation comes up a lot. I would argue that that's a good candidate for automation to maintain that digital thread and to ensure that your design model, at least when it comes to the application layer of the software, is fully consistent with the actual software. Next slide, please. All right, now I do want to make an important point here before my 2 minutes are up. Automation doesn't mean that you're skipping steps in the process. You can still follow the same process rigor, but just make it more efficient. And there are also tasks that even if you don't fully automate them, you can make them easier by using tools and models that can facilitate them. An example of this might be a requirements review, where certainly you're not going to have a machine review your requirements, but it might be easier if you can review the requirements in a model that allows you to trace the requirements to their allocations, for example, than just reviewing the words on paper without that context. And in some cases, machines can augment manual reviews for capabilities like using formal methods to detect design errors, for example, or static code analysis, not something you'd want to do by hand. Next slide, please. All right, because I started late, I will go over this quickly, but please do come talk to us at our kiosk or reach out to me on our Slack channel afterwards. If you want to see digital engineering and software standards for space come together on one large poster-sized page, I recommend that you take a look at our website. There are recommended workflows there for both the ECSS, European Space Standards, as well as the NASA NPR 7150, and of course DO 178 as well, if you're looking to borrow from the aeronautic standards. Next slide, please. All right, so to summarize, I think that digital engineering practices can make standards compliance easier. I recommend looking for that single source of truth for your design by making use of the digital thread. Automating tasks their machines are good at, that people might not be, but being mindful of skipping verification steps as you automate your workflows, or if you do that, at least do it intentionally and knowingly. All right, so again, my apologies if I was a little bit rushed, but hopefully we made up some time, and I don't know if we'll have time for questions now.
Thanks, Ossi. We actually do. Luis Rodriguez, who helped us put together the schedule, actually included 5 minutes of margin in between yours and the next presentation to help us catch up if we needed to. So we have 2 questions in the Q&A section. The first one is from Gerardo Cruz Ortiz, and it's, can we get a link to the There Is No Spoon paper? And I think if you, is that from Will Roper? Is that what you said?
Yeah, Will Roper. I don't have a link to it, but I think it's fairly well Googleable.
Yeah, that was my experience. I wanted to make sure I was the right author. So Will Roper, October 7th, 2020, There Is No Spoon, a new digital acquisition reality. It looks like you can get to that by, if that is the paper, I will throw that in the Q&A. All right. The next question is from Leonidas Cosmitis. Automate, and I'm sorry if I'm messing up any names. Automation requires tools to be qualified, but given that different standards are used, what can we do?
Yep. So qualified in reality actually means qualifiable. Just because a tool has been qualified for a specific purpose by somebody else doesn't mean that you won't have to qualify that tool in your own development environment for your own specific purpose. So, if a tool claims to be qualified, just keep that in mind. That usually means that somebody has qualified it for whatever standard they're advertising. But because you will need to qualify it for your purpose, you can just qualify it to the levels required by the standard that you're using.